Sergiy, it's a pleasure to have you speak. Thank you very much for organizing this and for inviting all of us. Your title is Classifications of Smooth Structures on One-Dimensional Non-Hausdorff Spaces. Please go ahead, Sergiy.
Thank you very much, Wilhelm. Thank you very much. My talk is devoted to some progress or some steps in the classification of smooth structures on these manifolds. Everyone knows that on one-dimensional, two-dimensional, three-dimensional manifolds, we have a unique smooth structure, whatever that means. And it happens that when we go to non-Hausdorff manifolds, they have actually uncountable number of non-diffeomorphic structures, and there is some formalism on that classification, and my aim is to describe several examples of how it works and actually what does it mean to classify smooth structures on such manifolds. So let me start from the very simple, from the beginning. What is a smooth structure? So suppose we have a topological space X, and by a chart we will mean the following thing. So we have an open subset, and this is open, and we have a homeomorphism, actually not homeomorphism, but even open embedding in some Rn. So this is an open embedding. This means that phi is a homeomorphism of U onto open subset of Rn. Yeah. And this pair U phi is called chart on X. And now let me say that X is a manifold if there is a family of charts Phi. This is a family of some I belongs to some set lambda, is a family of charts such that their union is X. So there is a family of charts which cover our topological space. This means that every point has a neighborhood which is homeomorphic to some open subset in some Rn. And this n may also depend on, so every phi I is maybe even a homomorphic and embedding into some other ni, depending on this dimension. So actually this means that X will have several connected components. You see that here I don't put any assumptions on which are usually assumed to be the second to have a countable base, and also to be Hausdorff. So this is just so actually sometimes these spaces are called locally Euclidean, but it is just simpler to to say that they are manifold. For example, what we can do on manifold. So our main aim is to make analysis on them. So this is, since we have analysis on Rn, so we have integrals, some smooth functions, and some many things. We want to pass to spaces which are not Rn but looks like Rn. For instance, what is a smooth function on a sphere or on a circle, something like this? The general idea, how we define what is a smooth function on a manifold. It is non-clear because we can do that only on Rn. But if we have a chart, so it is an open subset of X, and here we have phi, and here is a function here Rn. And then if we have a function here f into R, then we can say that f is, say, ck on U with respect to phi if this composition, if f restricted to U, composition phi minus 1 from phi U to R is ck. So I take this U, only this U, and I consider this map in this direction. So maybe it is better to write something like this. So here is P of U, he is a subset of Rn, and now when I have this is a restriction into R, and actually if this composition is CK, so I can measure smoothness only with respect to some charts. This is so these things are elementary, but I need to precisely define them in order to make precise statements about that. Well, but here we have a problem because because usually what is a smoothness? Smoothness, it is a local notion. So we can say about differentiability of a function at some point. And the problem, if my function is differentiable with respect to on this neighborhood with respect to this chart phi, that maybe it is not differentiable with respect to another chart psi. And if this map, let me say that this map is called coordinate representation of f with respect to u. Now, if we compare this coordinate representation, so we have a function here into R, this is f. We have, if we compare them, then we see that f in phi minus 1 is exactly f psi minus 1, and here is psi phi minus 1. This is again, this is very trivial, but what is essential that here appears here we have this map. This map is a map from psi phi minus 1 is a map from phi of the intersection uv into psi uv. It is called a transition map. And if we require that this map is, this is a requirement, that this map is CK, then if this map is CK, this also will be CK. If it also requires that the inverse, if both maps are CK, then our function will be smooth at this point, will be CK with respect to this chart, if and only if it is smooth with respect to this chart. And therefore, it is natural to consider, to put the following restrictions. So we say that the two charts are CK compatible if this map, the transition map, is these two conditions are called that it is CK diffeomorphism. So is CK diffeomorphism. And if we have this collection, now if we have a collection of UI phi, this is a collection of charts, such that their union is our X, then such a collection is called atlas. And if UI phi is CK compatible UJ phi j for all EJ, then the atlas is called CK atlas. And now, if we have a CK atlas, so all charts are compatible, then we have a well-defined notion of a function, of a smooth function. So a function from X into R is CK, let me say this alpha, with respect to the atlas, if it is F is CK with respect to each chart, or at least to any chart of this atlas. What is essential? And so our smoothness, we usually we work with subsets in Rn, and subsets in Rn have a canonical smooth structure. Namely, it is defined by the atlas consisting of a unique of the identity map. And always when we say about diffeomorphism or something like this, we usually imagine things which are in Rn. But actually, when we measure smoothness, it looks like some membrane over our manifold. So we have X, and over it we have some cover, and we measure everything smoothness with respect to this cover. Now let me go further, and then what is a classification? We have it is easy to see the following thing. So if alpha, let me introduce give the following definition. So let alpha and beta be two atlases, two CK atlases on X. Then I say that alpha and beta are CK compatible if their union is a CK atlas. This means that their charts are pairwise compatible. So the transition maps between not only what is CK atlas? Is it this means that transition maps between charts from here are CK compatible, and here is the same. And when compatibility means that their union, so any chart from here, any chart from here are also CK compatible. And this means that in this case they in some say no, this relation is equivalence relation. This is equivalence relation, and actually we can consider the union given an atlas A. We can consider the union all atlases which compatible with A and contain it. This union is it's let me denote it by like it's like a maximal atlas. We can consider maximal atlas consisting of all charts which are compatible with a fixed atlas. And this pair, this maximal atlas, is usually called that this is the same as is CK structure on our X. So the question of classification of so if you we have some equivalence relation on the set of all atlases, yes, and then we want to classify them. How to make this classification? Actually, this is a hard problem, and we have a continuous families of these atlases, of non-pairwise, non-equivalent atlases in this sense. Why? Because if you have any atlas of phi, okay, if you have one atlas family and H is a homeomorphism from my manifold to itself, then we can create another atlas, namely whose image consists of whose open sets are just images of these open sets, and phi is I should take a composition just with my H. Yes, so and it is easy to see that transition this map. So this if it is CK atlas, then this also will be CK atlas. So actually, when we apply a homeomorphism, then this homeomorphism will be actually a diffeomorphism, will be equivalence between smooth structures. This is an essential point. So actually, when we say about diffeomorphisms, that usually they are just homeomorphisms. And actually, every homeomorphism is a diffeomorphism with respect to specific smooth structures.
Yes.
And what is more better approach, so which makes less number of equivalence classes, we consider the set of, let me denote by C, the Kx is the set of all CK structures, which is the same as the set of all CK maximal atlases. And now what is the classification of smooth structures is exactly a description of the orbits of the action of the group of homeomorphism of my manifold on this space. So this, if this atlas is A, then let me denote this atlas by H. So classification of smooth structures is a classification of atlases up to the action of homeomorphism. Well, this is the general.
Sergiy, where do the parameters in this choice enter explicitly?
What?
The parameters, where do they enter in your choice of H?
Parameters? What do you mean?
Yes, for you said we have families of these inequivalent differentiable structures. So
Yeah, we take the set of all smooth structures, all maximal atlases, and now we act on them homeomorphisms. So this is exactly every homeomorphism allows to change atlas. And this
how do
gives
we know there's more than one element in this quotient?
what this is yes. How to prove this?
Yes.
This is no, actually for R we can prove no, we need to find some invariance or something like this which would classify them.
Distinguish, yes.
Yes, distinguish them. And for instance, for R, we can prove. So if you have any atlas here, no, how to prove the general statement for R. So if you have R and we have any smooth structure, so any atlas on it, well, then every atlas can be changed. So first of all, we can make this atlas consisting of open subsets of intervals, which are go one by one. Every open cover, no, look, if we have any open subset here, then we can have another chart which consists of V and restriction of phi on V. Well, so what we do, we cover our R, since it is R, we cover by intervals which overlaps only on which looks like this. And the next step is that if we have a pair of open subset of open intervals which looks like this, so one interval, this is another, and they have this intersection.
Yes.
Then there is a homeomorphism of this union onto this interval. So we can then next step is to replace this is a statement which allows to replace this pair of charts with only one chart.
I see.
Yes, and so the idea we just do this by induction, and finally every atlas reduces to the atlas consisting of one chart.
So the limit of these, the countable limit of these exists, of these modifications?
We made this in some way that this chart, that chart will be the same, will not change on the here. So we change it only inside, and this allows us correctly to extend it to all R.
Mercy.
This is the general, and finally we have a chart with atlas consisting of one chart. And after that, if you have any if you have here R with chart phi into R, and here we have R with another again with another structure, with another smooth structure with consisting also of one chart. Yes, and here then what we can do, we can now what I want the coordinate representation to be a smooth map, and I put it to be identity. It is smooth, and now this means that if I take this homeomorphism to be this one, if you have two smooth structures on R consisting with atlas consisting of one chart, and I take a homeomorphism from R into R, which is just like a transition map, then this map will be a diffeomorphism between these structures. Because if I go to local chart, then in the charts it is the identity map, and it is C infinity of, so it is of all smoothness which we have. This is the approach. This is a general how it is proved in the case of R. Well, and what I want to do is that I want to explain several examples how it is to present several non-Hausdorff one-dimensional manifolds for which we can make explicit computations and exactly describe the classes of describe this set. Well, so let me define two manifolds. One of them is the following one. So I take a real line, and I take I remove not remove point. I do the following. So what does it mean? That I just glue R. So let me take R by 0, R by 1, and I make a quotient. So I identify point x0 with point x1 when x is non-zero. So look, so I take something like this. I take real line here, I take real line here, and I glue them out of this of the origin. Yes, so this is a splitting of one point. Another very important in one-dimensional manifolds, non-Hausdorff, is the letter y. So I do similar thing. I take r by 0, I take r by 1, and then I quotient them by, so again, x0 is equivalent to x1, but now for x is negative. Yes, so this is the same. So essential point that I glue R with itself, but along open subset, not a closed. When I take closed, I may lose Hausdorff lose Euclidean properties. They maybe look very specific and why are essential, but they are essential in the foliation, the theory of foliation. For instance, suppose consider the foliation on the plane. The two foliations on with vertical lines. Well, and now what I will, let me remove one point. I remove it. And here, let me cut my plane. Then these non-Hausdorff manifolds are exactly the leaf spaces of these foliations. Yes, you see, because I cut one leaf and I get two connected components. So they correspond to this point. And here we have also two branches. This branch and this is another branch. Well, moreover, why are they essential, these manifolds, these two specific manifolds? You know that every one-dimensional manifold, by definition, has a cover with open subsets, which are intervals. But when we have non-Hausdorff manifolds, then we have some branch points. And actually, these branch points are, for instance, if I have something like this. So we have suppose we have some group of branch points. So we have from here, this goes here. For example, this goes, no, it's bad. For instance, this way, yes, and looks something like this. The principal things that when we go along interval and then we have a splitting, then this in 2 points. Then if these points belongs to the closures of another intervals, then we always have a letter y. If these 2 points belong to the closure of the same interval, we have let me denote this L and Y. We have so this pair is covered by L. So actually for non-Hausdorff manifolds, it is sometimes more natural to consider covers not just with intervals, but covers with these spaces, interval, then also letter L and letter Y. So from this point of view, we can slightly decrease the number of possible variants when we consider more general covers of this one-dimensional manifold. Well, and now how to make this classification? It turns out that here there is some general and unified technique which is actually can be formulated in terms only diagrams, and so the proof comes actually, it's like a proof in a category theory. So this is just a statement about some errors. But to go further, let me recall the notion was a double adjacent classes. let me say what this. So suppose I have a group G, and I have two subgroups A and B inside it. We know that we can consider something like G quotient by B or by A. This is the set of adjacent classes by B. And what I want to define is the set of, which is denoted in this way. It is the set of double adjacent classes. So what's this? This is the set of points of the form A, G, B, or A and B in for A and A, B and P. And G belongs to G. Yes. So you see, so we if you look at this part, then we just take adjacent classes of G by B. Yes, we consider right adjacent classes, and then we move them. We also join some classes which differs by element from A. So this set is not no, it is just more. So the equivalence classes consist just a union of adjacent classes. This can be also regarded as the following. So we have a natural action of the group A and B on G. Just again, the A, B here is I take G, and maybe I put here inverse. It does not matter. And we see that in this case, this is exactly a left action of this group, and the adjacent classes is just the orbits of the action of this group. Well, another thing which I need is the following things. We can consider more general, namely, if we take one group A, I want to define the following thing. So let me denote in this way. I take Z2 action on G into G. This is the same what was on the previous lectures. This is a rest product of A and Z2 on G, and the action is the following. So I take A, B, and epsilon, which is plus minus 1, and the action on G is A is what is it? Okay, A, G to the power A and B. So if he is minus 1, then I can also take the inverse of this group, of this element. So this is also the action of this group on G, and the classes, adjacent class, the orbits of this action will be denoted in this way. So I put here just plus minus 1. And now it turns out that these groups, these kind of objects, exactly are useful for classification of smooth structures on those, on one-dimensional manifold. So let me just formulate the following statement. So suppose X in general is a union of two open subsets. U and V are open. Well, and suppose U and V have CK structures. So on them we have some CK structures. For instance, when we have that letter A, L, then we have two charts. One chart which contains this point, and another chart is U, and another chart which contains this point. When we have letter A, Y, then we also have two charts. And what is essential that every homeomorphism from L into L, here is L, or every homeomorphism from Y into Y has a property that it leaves invariant U and V or exchange them. And here is the same. So we have two invariant subsets, or they are either invariant or they interchange. And suppose consider the general situation. Suppose I have a topological space which is a union of two open sets. Well, let W and suppose those sets have smooth structures. W will be their intersection, and assume that U and V have CK structures which coincide on W. So on every, what does it mean? This means that if I have U, V, we have restrictions, and the identity inclusions are CK embeddings. So on U we have common smooth structure, and now we have the diagram on this kind. So here we have an embedding. So we get a diagram of embedding of embeddings, and they are so here we have smooth structures, but they are not necessarily give a smooth structure on X. And the question is how to classify smooth structures on X which induce these fixed smooth structures on U and V. Well, and the statement is the following. So if I define CK of X and here I put UV is a set of all CK structures on X which induce the same structure on W. And consider the group of homeomorphisms of A, U, V, which preserve. This is a homeomorphisms X into X, which preserve my sets U and H of V equal V. Now consider the following. We have the following things. The group of diffeomorphism of U, let me take diffeomorphism of U, which live invariant W. So this is the set of say A, U into U, diffeomorphisms, which preserve my W. And similarly, I can define dV. Well, now next. Since V is preserved, then I have a natural restriction map, which corresponds row of A is just the restriction W. And consider the image of this group. So the image, let me denote it by X U W. This is the row of DWU. So this is a group of diffeomorphisms of V, which extends to a diffeomorphism of U. And similarly to the following, for W. Then the theorem, which we prove with my postgraduate student, Mykola Lysynsky. The proof the following, that there is a canonical bijection between how to know. So here I have UV. So this is the group of this is the set of CK structures on X which induce on UV those fixed structures, quotient by the action of the group of homeomorphisms which preserve UV, and the set of double classes V W diffeomorphisms W D X U V. This is a general statement. So those double adjacent classes, they classify smooth structures on this set with respect to the action of this group. In general, it is maybe it is not good and useful on usual manifolds, because the manifolds are the action of they are homogeneous. This means that we can freely move points by diffeomorphisms and interchange points by diffeomorphisms from U and V. And so this is not useful. But in the situation when we consider non-Hausdorff manifolds, at least two of these, it turns out that they are rather, this is very natural. So this U and V are always either preserved or interchanged. each one with another one. And therefore, this gives actually a classification in a uniform way, classification of smooth structures on L and U with respect to the action of diffeomorphisms group. So at least if I want to keep, just let us look on what happens on L. On this L, I have U is R, yes, and V. U and V is a real line, is just a real line, and their intersection is the complement to 0. And in this case, the group, what is the group of diffeomorphisms X of U of W? It consists of all diffeomorphisms. So this is a group of well, so here I have the group of all diffeomorphisms of R, and here I have the diffeomorphism of W. I need to consider the ones which preserve orientation and then preserve to this set. So the group of diffeomorphisms of this space contains naturally the group of diffeomorphisms of all R. So this can be identified with the diffeomorphisms of all R. And actually, so the smooth structures on L are classified by this double set. Again, to preserve orientation. And similarly, for when I take letter Y, then in this case, U and V is real line, but W is just the set of negative numbers. Well, and the situation is similar, but it allows, for instance, to present examples and even countably many examples of atlases which are not which are not homeomorphic, are not smooth structures which are not diffeomorphic, because in this situation this set is not consists of more than one element. Actually, it consists of countably many different elements. And moreover, what is interesting is that actually the proof here also can be applied in this situation when we join two charts. So in this case, actually, the proof of joining two charts into one, it also technically it also uses representation of element as in this way. Some elements in this way, and this is exactly so. It in some sense it repeats this general approach. Well, no, maybe I will stop here. If you have any question, please.
Sergey, can you give an example of two smooth structure which are not equivalent?
Yes. For instance, look. For instance, on L, yes, on this space.
Okay.
Consider two atlases. So we have the one is U open set, another is V. U, this is a real line. All of them are just we assume that this is a copies. So let me take here identity R, and V is given by the formula. X is maps into AX for some for positive A. Another atlas U ID R, and here V X into some BX. Well, B as not. If A not equal B or B minus 1, then let alpha and beta. This is two atlases. Then L with alpha is not diffeomorphic L beta.
So why is that?
Huh?
Why is that?
Because this
Yes.
they belongs to different classes. No, what is the proof? The proof is the following. So if you have a map, just one moment. So suppose I have a diffeomorphism from L into L, which makes the properties that U and H of V equal to V. What does it mean? Look, I have the following diagram. So V is contained in U, he is H. Yes, he is double. In this also the inclusion. He is contained in V, and he is also H. Now, if I put to coordinate representations, he is phi. For instance, I have phi U, psi U, psi V, and here is another atlas. Again, phi U and psi V. Well, here I have another atlas. Here is psi. Yes, this is also chart V, and W is contains here. Well, so here I have a transition map. Psi phi minus 1. Again, here is the same. So I put here U. This is the phi. Again, here is psi V. Well, W. And here is W, and this is included. And here is a map. And this is another, let me know this transition map GA, and this is transition map GB. Well, and let me denote this by A. What this will be A and B, diffeomorphism. If my H, if I have a diffeomorphism, a homeomorphism from L into L, which has this property, and if it is a diffeomorphism between structures, here is atlas beta, A and beta. If it is a diffeomorphism, this means that A and B belongs to a diffeomorphism of R. No, U and V are copies of R. So this is diffeomorphism. This means that we have the following identity between the restriction, between the transition maps, namely GB equals, look, if GB equals to GA, and here I should what I should take? I should take A restricted to W inverse, B restricted to W. Yes, but here this is A restricted to W, and here is B restricted to W. So I have this diagram, and you see exactly that identity. So these transition maps are related by restrictions of diffeomorphisms of all R to the intersection of those open sets. And this is precisely, this identity is precisely, maybe I should say more precisely. So if I have a smooth structure here, if I have a smooth structure alpha, and it is represented by minimal atlas U phi and V psi, yes, and then associating to it the transition map. This is a diffeomorphism of W. So this association, when I have smooth structure, and I associate to it a transition map. Then when I go to the action of homeomorphism, so this map induces a bijection on the following quotient sets. This is this is the formal statement, and it appears when we just consider this very simple diagram.
I see.
On the letter Y, no, just slightly complicated. If you want on the letter I, final things. The situation is more complicated, but I should put here something like this to A and to B. And here should be what else? So if I take just different powers, maybe so maybe modular, okay, minus, because this is sorry, incorrect. This means that the x, if x is positive, and x to the power a, since it is negative, I do the following, and here is the same. So diffeomorphism which is fixed on for positive numbers, and x and takes another power for negative numbers. So this is a homeomorphism, because charts are homeomorphisms. I take these charts, and with respect to these charts, these structures and this smooth structure are not diffeomorphic on the letter Y, on this non-Hausdorff. But if for the letter I can put here just multiples. So I can put something like AX and here BX, and that will be non-diffeomorphic structures on this L. This is just an example. No, we have a paper about letter L. And what we are working now is to finish in the paper about letter I and all this machinery.
Thank you very much. Thank you for the beautiful talk, Sergiy.